I'm Bruce Bugbee, president of Apogee Instruments and also professor of crop physiology at Utah State University. And in this talk today, I want to talk about modifications to our fundamental understanding of photosynthetic radiation. And I especially want to talk about the two edges of the cutoffs at 400 and at 700. Now this talk is a modified version of an address I gave 2 weeks ago at a controlled environments conference in Tucson, Arizona. It was a big conference, and I was asked to talk about this in an invited talk, but that talk wasn't recorded, so now we're going to record it for you. I love starting this off with the dark side of the moon. The prism divides up the colors, and we analyze them, and now we have LEDs as a very powerful tool to study these effects, photobiology. But we did used to use prisms a long time ago, so it's a really amazing change, the tools we have to study this. And of course, not only are they great tools for fundamental research, but they're great tools for growing crops too. So we're simultaneously doing work on them and studying their commercial effects. So to start with this, I want to start with sunlight and look at the ratios of color in sunlight. And I want to make the point that there's not a lot of photons down around 400, so the cutoff down here is less critical than the cutoff at 700 because there's a lot of photons at 700. So let's take a look at sunlight. Here's a classic curve of sunlight worldwide close to solar noon. This changes just subtly with time of year and time of day. It changes a little, but not a lot. Look at this, 3%. Let me turn on my pen here, and we can highlight some of this. There's only 3% of the photons right in here. The sunlight, because of atmospheric filtering, drops a lot right at 400. So even if we change the definition down here, in sunlight, this is a small effect. But we still want to look at this because it's important for LEDs as well as studies in sunlight. But look at over here, 18%. This cutoff makes a big difference for our measurements of photosynthetic radiation. Let's take a look at this for LEDs, which is why we're so keenly interested in this. If all we ever did was measure photosynthesis in sunlight, we wouldn't be so concerned about this. But look at our collection of LEDs. This was this beautiful slide showing the peak wavelengths, the classic things. If there's not efficient green, they're in the middle. But look at right here. There's some very efficient violet LEDs right near the cutoff, and the same thing up here. We have a very efficient far red LED, and they are being used in light fixtures to manipulate plant shape. So we really need to know if these photons are also photosynthetic. There's the violet, there's the far red, and because these are being used, we want to know. This graph was made by Paul Kasuma, who got his PhD with me in 2021. Last year he graduated. He's now at Wageningen University. So we've had a long relationship with Wageningen, sharing talent back and forth, and we've worked closely with Leo Marcellus there. It's been a great relationship. So what I want to do now is, first, let me emphasize two papers that Paul Kasuma wrote. These are not on the cutoffs, but they're on LEDs, and if you want to get state-of-the-art where LEDs are now and where they can go, search for Kasuma and Bugbee, and you'll see our referee journal articles come up. This one's called From Physics to Fixtures to Food, Current and Potential Efficacy. Where are they going to go in the next 5 or 10 years? And also, Photon Efficacy in Horticulture is a real detailed analysis of all the colors. So let's take a look at what we know about, first, the short wavelengths here, the efficacy. There's the part we're going to zoom in now on the next graph. Now we got 250 to 500, and here's our classic blue LED that's very widely used. This is a very efficient LED. It's used as the base phosphor for white LEDs, but we also have a series of LEDs right close to 400 nanometers, and it's real critical to know how efficient these are. They're being used in fixtures because they can have significant morphological effects on plants, triggering secondary metabolism, but do these photons cause photosynthesis? So to look at this, I want to go back and look at the historical studies on quantum yield from photosynthesis. This is from a paper I published 5 years ago, 2017. It's a book chapter. But here's the very famous McCree curve that more than hundreds, thousands of people cite this paper from 1971. But he wasn't the first to do this. A scientist named Hoover did it in 1937. Imagine the technology he had. That's 90 years ago to do this, where they got similar curves, not identical, but similar. And then a Japanese scientist, Inada, repeated this in 1976. At first glance, these are similar, but look at the area right here. McCree shows a big taper. Hoover shows a sharp cutoff. Inada shows a relatively sharp cutoff right down here in the UV. You can ask, why do we cite McCree's paper so much when there's other literature on this? It is because his paper is exceptionally well written, and it's a series of 2 papers, and they're very comprehensive papers. It's a great example to graduate students to read how clear his writing is in these papers. Here's Keith McCree. And as a young scientist, I had the opportunity to spend time with him. He came to Utah State University to give us a seminar, and he spent an afternoon in my lab. It was a great thing to know him. He died in 2014. So let's take a look at his studies right here on UV light. I'm going to blow this up. What McCree found was there was a large species variability in response to these UV photons. He studied 21 species, and I've taken from his data the one that was the most responsive to UV and the species that was least. And it turns out radishes was the most responsive, sunflower was the least, and if all crops were like radish, you bet we would move the goalposts. We would count these photons, but if they're all like sunflower, you can start to argue we should move it the other direction. But crops vary a lot in how fast this drops off in the relative photosynthetic efficiency. Now, sunflowers and radishes are not big crops in controlled environment, but lettuce and cucumbers are. Here's lettuce and cucumber. They're intermediate. They both drop quite fast right here, right close to 400 nanometers. This is McCree's data. Now, he had to use prisms and filters to get this data. It's amazing what he did given the equipment he had. Now fast forward 50 years to where we are today with state-of-the-art LEDs. So we set out in my laboratory to see if we could reproduce these curves using those violet LEDs that I showed you. State-of-the-art gas exchange equipment, state-of-the-art LEDs. And here's what we found. Now this was done by Shu-Young Zhen, who was a very talented young scientist. She got her PhD. She was a postdoc with me. She's now an assistant professor at Texas A&M University. These are her data in my lab. Remember that radish from McCree's data was one of the best. Look at that, radish is one of the best. Remember that sunflower was one of the worst. We repeated McCree's data using 50 years better technology, and cucumber was in the middle, tomatoes up there with radish. It's just quite remarkable that we were able to repeat his data. How about lettuce? Here's lettuce. These curves, they down to maybe 70% at 380 nanometers. This is a good point here. Marshall is a purple lettuce with a lot of anthocyanin, and that does not use UV photons well at all. Those anthocyanins are pigments that block the UV. We think the species variability is just blocking of the UV in the cuticle, which is for protective reasons. The take-home message from this is these curves drop off fast, and we don't see any reason to change the definition of photosynthetic radiation from 400 nanometers from what we have today, unless you're doing work with some species that can use them. And in that case, you ought to buy a spectroradiometer so you can precisely count these photons. So now let's move to the other end of the spectrum. Boom! Look at this effect. This is why this is such a big deal. This has been repeated now by scores of other scientists in laboratories. We know that far red lettuce makes the lettuce leaf expansion take off. And this is a picture of lettuce without far red and 10% far red. This is a big deal. Lots of literature on this. Here's the question. It's not controversial to say that far red triggers a shade avoidance response and makes the plants get bigger because they think they're in shade. That we've known for years. We know that happens. But is all of this dramatic improvement caused by photon capture and leaf expansion, or is some of it caused by direct effects on photosynthesis? And that finding is profound because remember, we've said since McCree, 400 to 700 is our range, but now do these far red photons contribute to that? That is an extraordinary claim to say that we should change our fundamental definition of photosynthesis. Now, for this extraordinary claim, we require extraordinary proof. And I bring in Carl Sagan, who in the series of Cosmos said, extraordinary claims require extraordinary proof. So what I'm now going to show you is the extraordinary proof that far red photons cause photosynthesis in the next few slides. For this, we start with papers of Xuyang Zhen, who was a young PhD student with Mark Van Eersel, who is a distinguished professor at the University of Georgia. Many years ago, Mark Van Eersel was a postdoc with me. And then, of course, recently Xuyang was a postdoc. Mark got his bachelor's degree at Wageningen University and had opportunities in the United States and came across the ocean here, although he maintains his ties with Wageningen. Xuyang and Mark first published a paper in 2017. These are all very reputable, are highly high impact factor, reputable journals. Journal of Plant Physiology, and I'm not going to go into all the details, but they studied the light reactions of photosynthesis in this paper and showed that the far red photons clearly improved the light reactions of photosynthesis. We'll come back to that in a minute. In the second paper, a year later, Physiologica Plantarum, they used laser LEDs at specific wavelengths to show that the photons, at least up to 730 nanometers, were improving the light reactions of photosynthesis. So, after this work in Mark's lab, I recruited Shu Young to come work with me because we have a canopy gas exchange system. It's a very sophisticated system, but it measures photosynthesis of whole plant communities continuously over the whole life cycle. There's 10 chambers, here's a few shown here. Using this canopy gas exchange system and precise measurements of canopy photosynthesis, we published a paper in Plant, Cell, and Environment, another high-impact journal. Far-red photons have equivalent efficiency to shorter wavelength photons. Implications for redefining PAR. This is now 2 years old. We kept going because we were interested in the long-term effects. This was short-term effects with and without far-red on canopy photosynthesis. So we did a study with long-term effects through the whole life cycle, and again showed these far-red photons had equivalent efficiency to the shorter wavelength photons. And this is in Frontiers in Plant Science. So we got 4 significant journal articles now from 2 different laboratories showing the value of these. Because of this work, most colleagues have now switched to including photons up to 750 nanometers as photosynthetic when they're doing studies in controlled environments. It doesn't just stop with our papers, because 2 other research groups that study this have now reported on this. Zhao et al., 2019. Terashima is a well-known scientist. Plant and Cell Physiology, well-known journal. These are supporting papers. So the technical studies on this are providing that extraordinary proof that we need to change our understanding of far-red photons. So, to make a claim like this, it's not adequate to just say you have empirical evidence that this occurs. You need a mechanism coupled with the empirical evidence. And as I say, our understanding of how the world works requires a coupling of measurements and models and data and theory. So this is the theory that supports that. Without the theory, maybe 400 years ago we said the moon is made of green cheese. Well, that must have been because of reflected light. You know, that's a common myth. And people said, you're nuts, you know, there's no mechanism behind that. And think of all the observations we have without mechanisms. That usually means the observations have something wrong about them or they're incomplete. But in the case of far-red photons, I go to my favorite Twin Towers diagram of how the light reactions of photosynthesis work. So we know from the Stark-Einstein law, our buddy with the wild hair, 1 photon excites 1 electron. That's why we count photons. A photon comes in, it hits the light reactions, boom, it excites an electron. That electron cascades down in energy and it makes ATP. Another photon comes in, boom, another electron goes up, and this makes NADPH. This is photosystem 2, this is photosystem 1. Water is split here in the photosystems, but this is a really good example of the energy state of photons exciting electrons in photosynthesis. Here's the key. This guy over here can be excited with far-red photons. We've known that for 50 years, and that is called the Emerson enhancement effect. That these photons can excite electrons in photosystem 1. And in fact, if you don't have any far-red photons, these 2 photosystems that run in closely synchronized process can get out of balance. So this is the theory that underlies this. There's many ways to show this, but I've liked this Twin Towers diagram, which I got out of a photochemistry book, to show where the photons come in. So now let's take a closer look at this. Back to the full sunlight spectrum. So far, we have only shown this under electric lights, where we add far red and we take it away. That's compelling evidence. But if it works under electric lights, it should also work under sunlight. The effect should also be present under sunlight. So now, in the final series of studies, and this is with Shu-Young Jen, Mark Van Eersel, and myself, we undertook to make these measurements in sunlight. Now, there's 18% photons out here, so that's what we're looking for, is an 18% effect. To do this, we filtered the light, bought special filters that cut this off. And there's our filter, far red filter. It was a very nice filter, cuts this off cleanly at 700. These photons are gone. This filter also cut out the UV. Now remember, we hypothesized that UV is not going to have a big effect. That does. So we added measurements with a third filter that only filtered UV. This is blocked, let this through. When we put the UV filter on leaves, and when I say we, that means Shu-Young did the work making the measurements in the trenches, less than 1%. So these photons, as predicted, had a small, blocking them had a very small effect on photosynthesis. That's part of the reason we say 400 cutoff at the bottom is a good cutoff. We see no reason to change that. But what happened up here? With the far red filter, P-net decreased 12%. Now remember, there's 18% photons up here. And there's a number of issues up here with how high was the light, what was saturating. This number doesn't precisely match this, but that's a big decrease in photosynthesis. And if it's not caused by this, you got to hypothesize something else does it, and it wasn't temperature. We measured a number of things with this research. This data shows that far red photons are important in sunlight as well as electric lights. But now let's look at one other case for plant ecology. Understory crops. When we start measuring global photosynthesis, what happens to these plants down here that get filtered light? The far red light is transmitted to these plants, and if we make a spectral curve of this, this is filtered, this is transmitted. So suddenly, for these understory crops in here, wow, more than half of their photons are far red photons. This has huge implications. Are we only going to count these photons in here green, or are we going to count all of those photons? So we made measurements of understory crops filtered by leaves. What did we find? Here's the filter. Applying that filter, we block this, let the green come through. P-net decreased 40 to 60%. This is a huge effect, and it further emphasizes the value of far red photons in global climate change research, our global climate change models. This is a big finding. And throughout all of this work to collect these data, we knew it was a big finding. So we published this in a very high impact journal called New Phytologist. This has an impact factor above 10. It's reserved for groundbreaking research. Look at the date, July 2022. This is a recent publication, Photosynthesis in Sun and Shade, the surprising importance of far red photons. So I refer you to this paper for the details of how we did the work. We got a lot of excellent reviews from some prestigious photobiologists in this, and they were very appreciative of our work. So the collective body of evidence indicates that we need to be counting photons from 700 to 750. So what does this look like now? Back to the McCree curve, the classic McCree curve. Once again, we don't see evidence to move the goalpost here, but up on this end, remember McCree did not do synergistic effects. This was one wavelength at a time, and had he done synergistic wavelengths, far red and shorter wavelengths together, the evidence is that he would have seen the same thing we did. These are synergistic with this, and so now the new definition adds this out here to the curve. So the old metric, there's 750. The old metric was called PAR. The new metric we've been calling ePAR, for extended PAR. And we're recommending people report both of these in their studies, but they focus on ePAR as the fundamentally best metric. And multiple other laboratories are doing exactly that. They're counting these photons as photosynthetic in their research. This has a number of implications, and I want to review those now. So the move from PAR to ePAR. Number one, efficiency of fixtures. Are we going to count these photons in LED fixtures? And all the evidence is we should be counting them. ASABE does standards for this, and so far their old standard is 400 to 700 nanometers, but they're meeting again to revise this, and people on this committee have told us we need to change the standard in the light of all the evidence we now have for ePAR as an improved metric over PAR. So this is one big implication of this. Second one is the Design Light Consortium rates lamps, and they're becoming a go-to standard for efficacy of LED lights. If they do not count far red photons, they penalize the lighting manufacturers that add far red to their lights. So they're looking at making this change too, and they probably will have two metrics, PAR and ePAR, to help people select the best lighting fixtures. And then finally, in portable photosynthesis systems, which we use a lot to measure photosynthesis, they use LEDs to light the leaves, but historically, they've not had far red LEDs in the heads of these portable photosynthesis systems. So that means they get artifacts, and they underestimate true photosynthesis under sunlight. And it also inhibits further studies on this because the LEDs don't include far red, but there's one exception. PP Systems has now come out with a new gas exchange. It's called the Cirrus 4, and that one has far red LEDs in the head. So it's continuing evidence that the world's changing to a new definition. Many people use a LICOR portable photosynthesis system, and we're told that LICOR is looking to add these far red LEDs in the head of their meter as well. This is the end of the story, but we need to help you make these measurements, and to do that, we need a new suite of sensors. So, Apogee Instruments came out with, first of all, they've come out with an ePAR sensor. Now let me draw, here's the sensor, silver, looks like this. Let me draw this on the board. Here is, we count the photons equally. Here's 400, 700, PAR, just like the slide shows. This sensor goes to 750, and it's called ePAR. Extended photosynthetic active radiation. In sunlight, this adds about 18% to the total photosynthetic radiation. Under electric lights, it may only add 3 or 4% unless you're using far red LEDs, and now that under electric lights, it can add 18% as well. Because of this effect, and because we have the traditional PAR and the new ePAR, Apogee also made this sensor. It's a black sensor. This is hooked up to a microcache data logger. This sensor is called the PAR-FAR sensor. Creative names for sensors, and it has 2 detectors in it. So it gives a reading for PAR, and it gives a second reading for just this radiation right here, and then of course you can add them together. So it gives you 3 numbers, this reading, that reading, and the sum of both of those. This is a little bit more money because it has 2 detectors, but allows users to separately measure both of these. And then finally, lots of people want integrated meters for daily light integral. This is a relatively new meter that it has a microprocessor inside, and it gives instantaneous ePAR, and it also integrates the total of the day. It stores it in memory. You can get daily light integral for the past 100 days with this sensor, which comes in both the old PAR version and the new ePAR version. Of course, all of these sensors can be hooked up to data acquisition systems. They don't have to be hooked up to meters. This is an exciting time. Think of people in greenhouses that have mixes of supplemental light and this. If we don't include this, we're going to underestimate the photosynthetic radiation in greenhouses. So not only do we feel like there is solid empirical and theoretical evidence to change to ePAR, but we've also provided the sensors to facilitate making that change. Thanks for listening. We'll catch you again in the next video.